as I was saying, the midterm is after 1 week from now on Thursday. It's gonna be this in the same place here, like same classroom. It's gonna be 75 minutes, and it's gonna have only one questions on the flow part, and the rest of the exam is gonna be on the work and energy and the impulse and momentum, and maybe one small questions on the dynamic part from the last lecture. Okay, so for the dynamic part, I just want you understand, please keep attention to this, okay? Alright, so what we did in the dynamics part, we have an equation. This equation, the general form, keep attention to this because this is might be worth some point in the exam. mu double dot plus cu dot plus ku is equal to a force, okay? So in the left-hand side, you have the resisting function, okay? Like you have the building, like for example, let's say that our building is something like this. This is the building. The building has bunch of masses. So this is the mass, for example, M. So this is how we get this, the mass, right? Maybe the building has damping, something like this. Certain way for damping. So this is how we get this part, the damping, okay? The building has stiffness. It's coming from the columns, coming from the shear walls, coming from the bunch of elements inside our building that provide masses to our structure. And this, how we get this part, okay? So this is very, very basic. This is what we call the resisting function. Resisting function, right? So that's the structure, like the structure that we sit in right now. There's no any earthquake loads, there's no wind loads, right? So this part is zero, right? There's no force on the structure, but there's masses, our own weight of the structure. There is damping the structure has a potential damping. If an earthquake happens, it can damp the force in a specific way. And it has a stiffnesses because all these columns has a stiffnesses that hold this structure still without any failure. So this is what we call the forcing function. Okay? So for the forcing function, if you have an earthquake, so this is going to be something, for example, like this, and I told you before, earthquake is a force over time. Sometimes earthquake lasts a few seconds, some earthquake lasts a couple minutes. So time with the force F, but F is a mass multiplied by acceleration. So we usually, since the mass of the structure is constant, we make it as a function of the ground acceleration. How much ground acceleration this earthquake is shaking the ground. So for example, the earthquake starts very, very small, tiny, and then grow bigger until it gets to its peak, and then it dies out. Or maybe having some aftershocks and become something like this, okay? Right? So this is an earthquake. However, sometimes this force cannot be an earthquake, it can be any moving load. Maybe the function of the force over time can be something like this, like a sinusoidal wave, all right? Can be any shape. So the forcing function can have any shape. Actually, sometimes it can be constant over time, maybe 10 ton applying dynamically on the structure, okay? So if you guys remember, if we don't have the damping, because this is very, very important, if there is no damping in the equation, or we are neglecting the structure, damping, potential, so this system is called undamped system. Okay, when we solve the structure without damping, it's called undamped system. And if the forces on the structure are zero, it's called free vibration. Okay, so if this is not there and this is not there, so it's called single degree of freedom, undamped under free vibration. But if this there, so it's a damped system. Okay, all right. And if this there, it's not free vibration, it's a forced vibration. Okay, so we all understand that. But the mass part and the stiffness part, they always stay there. Okay, so right now we have a structure. This is the resisting function. This is how the structure is resisting the dynamic load, and this is the dynamic load, either earthquake, either wind, either whatever wave that is there. What we need to do? What we need to do? We need to find if this building is exposed to this earthquake, how much displacement is this building is gonna have? Like how much? Like I have my building is like this, and then an earthquake starts shaking, so my buildings start to move. I want to know what is the maximum displacement that this building is going to have, and how can I know it? That's how we spent 40 minutes last time solving the differential equation of the structure to find the equation of U. So the purpose of structure dynamics is to find U. So let me tell you, if an earthquake was this forcing function, do you think that the U that the building is going to have is a constant? Like, you have a forcing function, like the earthquake starts small, so something like this, and then it shakes very fast, and then it dies out. So definitely the displacement changing over time. So it's going to be a little bit small at first, and then gets bigger at the peak, and then dies out. Maybe the building can fail, like when it gets to maximum displacement, then the building fails. Or if the building holds itself, it's gonna be a little bit and then gets to the peak and then dies out. So when you solve for an earthquake, the building displacement is gonna be, right, like this building got exposed to an earthquake like this. AG, and this is the time. And the earthquake is something like this. The response of the building is gonna shake and it's gonna make a displacement like this, and this is U. This is the maximum U, okay? But how we get the maximum U? I need to solve this equation at each time step. So I divide this earthquake to a specific time step and get like very, very small time steps and get what is the force of the earthquake. What is the force of the earthquake? So I put this as the smallest steps and then I integrate all these steps and then find the final displacement here. And the final displacement is gonna be something like this. Like this is the time, and this is U. And if you get the displacement, it's easy to get the velocity, right? If I know the displacement and I know the time, how much it takes the structure to get this displacement, I know that the velocity is the displacement over time, and I can get the acceleration, which is the velocity over time. So if I get U, I can get U dot and I can get U double dot. So I can get how much acceleration this structure is gonna have. So, and it's gonna be something, for example, like this, right? So what is the difference between this and this? Both of them are acceleration, okay? But this acceleration is the acceleration of the ground that comes from a specific earthquake that has a specific source point. It transferred to a specific area and shakes all the buildings in the neighborhood. Maybe hundreds of buildings in the same neighborhood are gonna be exposed to the same earthquake acceleration. However, this is not quite right because the earthquake acceleration gets dissipated once you be far away from the source. The more far away, the earthquake is gonna be less, and also depends on the soil type. But let's assume this is gonna be a little bit of variation that we can consider it's a constant on the same neighborhood, same Miami. All Miami building got exposed to this earthquake. All the ground is shaking with the same ground acceleration. But every building is gonna have different acceleration. The buildings that are small are gonna have an acceleration different from the buildings that are big. Is gonna have different displacement. That's what I want you to know. There is a big difference between the ground acceleration that comes from the earthquake and the building acceleration, which is a response to this earthquake. And how we get this? By solving this equation. Here's U double dot. How we get this? We get verse. We solve it for U, and then we differentiate U to get U dot, and we differentiate U dot to get U double dot. Look at the notes from last time. We have like 3 pages, how to solve this equation, how to get U, and then I differentiated U to get U dot, and then I differentiated U dot to get U double dot. So that's what is the purpose of structural dynamics. Is to solve the structures under dynamic load to get the responses. And this is how the responses is. And as a structure engineer, I'm not interested in all this. all these small displacement I'm not interested in. I'm only interested in the maximum displacement, U maximum, or U dot maximum, or U double dot maximum. I'm interested in the maximum displacement. So the purpose from last lecture is summarized here. You have a resisting function, you have a forcing function, and solving this is gonna give us what is the response of the structure, what is the displacement of the structure. And each building in the same neighborhood is gonna have different response. Why different response? Because every building has different mass, has different damping, has different stiffness. Okay? Even they are exposed to the same earthquake. Okay? Alright, but what if our structure is under different force, like the force is like this, so definitely this is gonna be changing. So based on the forcing function, this all is gonna change. What if the force is zero? There's something, okay, well tell me, if a building doesn't have any force, how it can have a response? Like assume a building got a force and then you lift this force. The building is gonna have a little bit of free vibration without any force. And what we are interested in, how does this free vibration look like? Okay? Alright, so this is a summary, and I want you to understand this very well. We have 6 pages notes. Understand them. I'm gonna ask you not to solve lots of mathematical things. I'm asking you in this concept. What is this equation? What is the resisting function? What is the forcing function? What this means? What is the difference between the ground acceleration and the building acceleration? So you need to understand these basics. All right, does anybody have any questions so far? Okay. All right, so let's start a new topic. Yeah, I was saying an announcement, I only announced the midterm. So next Tuesday, we're gonna have site visit to the Wall of Wind. Wear closed toe shoes and hard hat if you have it, bring it with you. So it's gonna be a lot of fun. Like you will see how real testing. Wall of Wind is one of the biggest wind testing facilities in the U.S. and maybe in the world. So it tests full scale buildings. So you will see how real test and actually changes the standards of design wind loads. Lots of the wind load design standards has been changed, and some of these changes, some of the contribution comes from research that has been done in the Wall of Wind. And also for your information, FIU is gonna build a much bigger facility. I believe in the next 10 years. It's under design right now. Just for your information, it's gonna have not only wind, but also it's gonna have a storm surge and waves. Like it's gonna be a huge building that you have the building on a turning table, and a water is hitting the building while the fans is pushing wind. So you test we are simulating the combined impact. Like a building on the coastline is getting hit by a wind and a storm surge and wave. Storm surge is like the flood depth, so when the sea goes up. And the waves on the top of this surge is hitting the building while the wind loads is impacting the building. So lots of things good happening there. So if you are interested in natural hazards and how they impact the building, even if you are gonna work in Florida, wind is a very, very important load that you need to consider. So maybe a visit to a Wall of Wind is gonna help you to. I know that you guys right now, some of you, we all are gonna be civil engineers, but some of you are gonna become, I wanna be a structural engineer, I wanna be an infrastructure engineer. Some of you, I'm gonna be a geotechnical engineer. So right now, I understand what make up your mind, but at some point, you will have to pick what you love to work at. And actually, that it changed. Like when I was young and I'm the same age, I wanna be like a tall building designer. I wanna do this, tall buildings, fancy, blah blah blah. And I did my master's in seismic and lateral load design of buildings and all that. But at some point, I discovered that there's something that are much better, not much better, but it fits me more. Or when I studied it, I found that it's much more interesting to me. Like I went into natural hazard. Like 7 years ago, changed everything and moved to natural hazard to study how they impact building, how to calculate the vulnerability of an entire community to a specific hurricane or a specific flooding. So things can change, but be open to explore your options, because don't make up your mind, oh, I wanna be for example, no offense, like I want to be a hydrologist. Hydrology is a very, very impressive field. I love it. But you didn't explore other options. You didn't see what structural engineers can do, what infrastructure engineers can do. So explore your options, see what you can be good at. So when you have an opportunity for a visit to a wall of wind or to an internship in something, I did internship in my fourth year, because my engineering program was 5 years. So in my fourth year, I did an internship in geotechnical engineering. And I loved the geotechnical engineering. I was about to pursue my career in geotechnical engineering. But then at some point, oh, structural engineering is much better. So I went for structural engineering. So explore your options. Don't close doors and don't have like this mentality. Explore your options. Try this, try this, try that. Make up your mind. This is what I want to be. And also look what the market needs. Maybe the market needs this. This is a factor, not the whole 100%, but this is one of the factors, because some engineers outside make a hell of a lot of money out of other engineers. Like, for example, like if we are talking money, who's making the most money in our field? The forensic engineers who go like assess the building, assess the damage, and do retrofit plan for a building, like buildings that are 50 years old. Foundation is messed up, the structure needs to be retrofitted. So you do a retrofitting plan, they make a lot of money. Also, engineers that are into insurance industry, like who, for example, calculate the building premiums. Like you are saying, you guys are living in a house and you are paying insurance, wind insurance or flood insurance. Who calculate this insurance? Engineers. Like engineers calculate hazards and probability that the hazard happened, probability of the damage happened. How we calculate probability of damage? We need to know resistance of the building. We need to know how the building aged over the years. And it's not about constant thing. We do lots of probabilistic analysis. You guys study probability? So at some point, this probability mixed with structural engineering makes lots of things. So, and based on the probability of damage that can happen, based on a specific event that can happen from the middle of nowhere after 20 years, this building is gonna have $100,000 of money that you need to spend to bring it back before the hurricane. So we distribute the $100,000 over the 20 years or over the lifetime of the building, and you keep paying this premium until something happens, and then you take the money back. So all this is done by engineers. And how this is start, like you need to have a background in natural hazards, you need to have a background in probabilistic analysis. Most of the people who work in this field, they need to have masters or PhD, and then they go work for risk modelers company, and then you move them from risk modeler companies, then they go to insurance company, and they make me maybe double or triple the engineers that go and design buildings. Okay, so study your options, know what is best for you, and then explore things. There's lots of variety of things that you can do as a structural engineer or as a civil engineer, and then pick the one that best fit for you. So that's your advice. So maybe the visit for the Wall of Wind can help you to explore one of the options. Yeah.
Yeah. Will this be the only time you take just the Wall of Wind?
Yeah. Just it's not like even if they are not, we are not gonna test something like you are not gonna see. Even they are testing something. I watched some of that. You are not gonna see the wind. But there's some fancy wind tunnels. They put like powder or something so that you can see. But you are just see the facility, how the fans look like, how the turntable look like, how they put the samples, stuff, so you can understand how the testing facilities look like. That's it. It's not, yeah, like, fancy, but it's good. It's good to go there. All right. Okay, so let's get back to dynamics. So over the last 2-3 months, we have been studying the dynamics of particles. We studied fluid dynamics. We studied structural dynamics, but we didn't study the dynamics of rigid bodies and how rigid bodies are going to be different from particles. So chapter 16.1, planar rigid body motion. Okay, so what is rigid body? So rigid body is a solid body which doesn't deform. So when I talk about rigid body, so this is not a rigid body. Okay, when I talk about rigid body doesn't deform. All the points on this rigid body, if this body is moving this way, all the points should move this way or move this way. If a point can leave the other point, like this point is still, and this point can go up and down, so this is not a rigid body. Okay, so it's a solid body that which doesn't deform. And there's different types of motion that can happen to rigid bodies. So let's explore them. Yes?
Can you give us an example of a rigid body?
Yeah, so rigid body, this is a rigid body, like this one. This is a rigid body. So all these are rigid bodies. However, sometimes like what is the difference between particles and rigid bodies? Sometimes when we consider a rigid body as a particle, okay, like if the rigid body is moving in a translational motion, so we can deal with it as a particle because all the points are moving the same way. But if we have this rigid body, it's fixed from here, so you're able to fix a point, and it's moving this way, so each point here is going to have different velocity. So that's why we need to convert from the mentality of particles to rigid bodies. However, some rigid bodies like the car, do you guys remember? The car has multiple rigid bodies. But the car is moving constantly. Every point on this car having the same speed at the same time, nothing is changing. Okay? So we consider the whole car as a rigid body. So we are going to find out why we separate rigid bodies from particles. Okay. So rigid bodies can have different types of motion. So it can have, their motion can be, number one, translation. Number two, rotation. Number three, general plane motion. So if it's a translation, so we are going to deal with velocity, acceleration, and the position of the rigid body. If it's rotation, so when we say rotation, everything is going to be angular, not the regular ones. So we are talking about angular velocity, angular acceleration, and angular position, theta. If it's a general motion, it's going to be a combination between these two. Okay, so let's explore the different motions. So let's number one, start with rectilinear motion. Alright, so if I have a rigid body, like a general one, something like this, and this is point A on this body, and this is point B on this body, and it undergoes a rectilinear motion, and this body was able to move this body moved this way and came to this position. Same body, and this is point B, and this is point A, B, and A. So the velocity in this body are the same for all the points on this body. So this is VA, and this is VB, and I mean rectilinear motion, so it's moving linearly, and VB as a vector is equal to VA as a vector. So what is special about this motion? That the velocity vector are equal in magnitude, VB equal VA, equal in magnitude, direction, and also they are parallel to each other. So this is a rectilinear motion. So let's, number 2, talk about curvilinear motion of rigid body. Alright, for curvilinear motion, same body, and this is point A, and this is point B, and this body is gonna move on a curve, something like this. Okay, so it's gonna be, for example, somewhere here, and this is point A, and this is point B. Alright, so VA is always tangent, the V is always tangent to the path, so this is VA vector, and this is VB. And this is VA. So, and then when the body came here, the velocity is gonna be different. This is VA1, VB1, and this is VB2, and this is VA2. So what is different here? First, the VA1 is equal to the VB1, and VA2 is equal to the VB2. But here is not equal to there. And the omega of this body, when I mean the omega is like the body is rotating about itself. Okay? Is it spinning? So it's not spinning. It's the body as a whole is moving like this. Like, do you guys remember a car is moving on a curvilinear curve? So this is the same thing. Like a car is moving on a curve. The car is not spinning around itself, it's just moving. So the car has a normal acceleration. Okay? So it has a normal acceleration but it doesn't have omega. So omega is equal to 0. Here, the normal acceleration, definitely omega is equal to 0. And there is no normal acceleration because it doesn't move on a curve. But here, the normal acceleration doesn't equal to 0 because if a car is moving on a curve, there will be a normal acceleration. Does anybody have any questions so far? Okay, so this is for the curvilinear motion. So all this sounds familiar, but let's do something new. Fixed axis rotation. So number 3. Fixed axis rotation. Side thoughts, please. Do you guys have any questions? Yeah, sure.
At some point, A and B didn't have the same speed. That's why they turned. Or
This one and this one?
no, yeah, below.
Here?
A and B. At some point, they didn't have the same speed, right?
So A and B, like if the body's moving on a curve, so at each point, like velocity vectors are equal at every point, but they change over time. Okay, so if they have an acceleration or something, so they change in magnitude, maybe they change in magnitude and direction, maybe they change in direction. Okay, you see, this one is moving this way, this is moving down. So they keep it changing the direction over time. But this one has the same magnitude in the same direction all the time because it's rectilinear translation. Okay, so this one is going up, this one is going down. That happens when a body is moving on a curve. And what I'm talking about the points on the body. Same thing, if you have a point here, this point is gonna be something like this. Here's the velocity here, and here's the velocity down there. So we are talking about multiple points on the same body.
Is it possible to put this monitor?
But what?
The monitor.
Oh, okay, sorry.
Perfect, thanks.
Alright. Okay, so let's do the fixed axis rotation. So if we have a body like this, okay, and this body is pinned here. So there's a pin here. So this body can move like this. Okay, bend here so it can move this way. This is called fixed axis rotation. And let's say that we have, here's point A, and here's point B, okay? And this is moving with an angular velocity. Right now we have angular velocity because this body is moving around a specific point. It might be bent from the middle, it might be bent from at the end, so it doesn't matter. Okay? So, and it has omega like this. Okay. So, the velocity at any point on this body is equal to the omega cross product the r vector. What is the r vector? The r vector is the line from the bend point to the point of interest. So for example, let me ask you, if this body is moving with an omega this way, okay, like I left from here and it's moving this way, is the velocity, what is the direction of the velocity? It's going this way or this way, or point P? It's going down or going up?
Going down.
Going down, absolutely, right? But let me ask you, is the velocity at A is gonna be the same as the velocity at B?
No,
Why?
because it's farther away from.
The R is different, right? Yeah, far. A is far, excellent, and B is close, so they have different R, and that makes sense. Like, let's say that this body moved with an angle, like theta is equal to 30 degrees. So this line become like this, okay? So this is 30 degrees. B is gonna, A is gonna be something like this. It's gonna come here, and B is gonna be here, right? So B cut smaller distance, A cut bigger distance at the same time. So you both move at the same time. So A cut, for example, 2 meters or 2 meters in 2 seconds, and B cut 1 meter in 2 seconds. So definitely A is moving faster than B. Even they both are at the same body, but they are bent at different locations, and the R is different. So here, this is RB vector, and this is RA vector. So if I want to find VA, it's going to be equal to the omega, they both have the same omega, but this is crossed by RA vector, and VB is going to be the omega crossed by RB vector. Okay, but how we knew the direction of the velocity? Like we said that VA is going to be this way, and VB is going to be this way. And that's actually, we anticipated this because that makes sense. My body's moving this way, so both of them are going this way. That's the direction of the velocity. But how mathematically, using the omega and the r vector, can I know the direction? So this is a cross product. Do you guys remember? When, for example, this is I, J, K. If I want to find out the cross product of omega and r, so if I'm crossing product I and j, so use the right hand rule and move from I to j, so the cross product is going to be k. If you want to cross product j with k, so with the right hand rule, you will find that the I direction is this way. If you multiply k by I, it's going to be this way, so it's in the j direction. So let's do it here. If omega, my body is rotating this way, okay? What is the direction of omega? It's rotating this way. The direction of omega was right hand rule. So this is how omega is rotating. So the direction of omega is this way. And you should know that. Okay. So if you have, for example, omega is counterclockwise. So the direction is going to be this way. Omega. If omega is clockwise, this way. So I use the right, sorry, this is gonna be on the other hand. If omega is this way, my right hand rule, like this way, and so that means that this is the direction of omega. This is how we get the direction of any rotating motion, okay? This one is gonna be this way, so this is the omega's direction, all right? So if omega is rotating around this I, so it's gonna be this way in the I direction. If it's a j, so that means the rotating is this direction, so it's in the j direction. If it's k, so it should be rotating this way in the k direction. So let's find out. Omega is rotating this way, so the direction of omega is gonna be, is the red. So omega direction is out of the plane, like going inside. this way. So this is example. This is omega. I'm making this arrow. That means it's not in the same plane. It's going inside. Okay. All right. And I have r is in this way. So when I cross omega and r out of the plane, like, okay, so that you can understand it. So omega is going this way, r is this way. Okay. So when you multiply them together, so it's gonna be this way. So v is going down. But if omega is on the other direction, this way, and you multiply them together, so this is gonna go up. Okay, so that's how the cross product look like. It's if we want to make it at 3D, actually omega is going this way in the negative I. This is omega, and it's going outside inside the board, and r is on the board, which is like, no, it's much harder. But you guys understand it, right? Did anybody didn't understand it? It's just like you have omega is going inside the board, and this is on the board, something like this. So when you multiply them together, so it's gonna be like the velocity is going on this direction. You can put omega here if it makes sense to you. Like if you say that this is the r direction, and the omega direction is out of the plane. Okay, like I don't know. Let's make it as 3D as much as possible. This way, this is omega. So this is perpendicular, this is going inside, like omega is going inside this way, and r is this way. So when you multiply them together, so it's gonna be, v is gonna be going down. So imagine it like this, and this is omega, and this is r. When you multiply them together, v is gonna go down, okay? All right, so this is how we get them numerically. Okay, and the last one that we have is the general plane motion. General plane motion that you have, for example, a body like this, and it's not making translation, it's making combination of translation and rotation, and this body came, for example, here. So this is point P and this is point A. B came here and A came here. That body make a translation and rotation. So we are gonna study all these bodies movement and see how can we deal with them. Let's just start first with the rigid body translation, how we can get the rules. Sir? Yes?
For the graph K, is the blue arrow the wrong way?
Should be this way. If it's counterclockwise, it should be going down. Use your right hand, not your left. So this one is this way, this one is this way. I make this one going this way. Like this, okay? But if it's rotating, I'm not sure, maybe it's a little bit confusing, so let me make it like rotate. Like this, I'm not sure, it should be 3D and it should be
And the
this
other
one.
two are clockwise.
Hmm?
The other two are clockwise.
The other two are clockwise?
Are they?
Well, it needs to be in this plane, but the thing I is out of the plane, so this is counterclockwise. Clockwise. This one is still counterclockwise. And this one is still, all of them are counterclockwise. Like you have to, okay, so, let's start with rigid translation, chapter 16.2.
You say Abu. أتذرب فيه ما
Alright, so if I have a body, a general rigid body like this, and this is my xy coordinates, okay? So if I want to define the position of this body, or the position of any point in this body, I should have and axes, references, and then move from the origin of this reference to point A. So this is going to be the position of point A, and we say this is RA. This is position B, and then I move from here to here, and this is going to be RB. But before I do this, do you guys remember, if I want to move from point A to point B, there's different ways that I can go from point A to point B. I can go directly, like this, or I can go to a transition point C and go this way, or I can go all roads leads to Rome. Okay? So if I want to describe RB, there's different way to describe how I get to RB from point A. I can get right away using RAB, right? Or RB can be equal to this vector plus this vector. So it can be RAC plus RCB, or it can be, let's call this B, RBC plus RAB. And this is RBC. Do you guys have a problem with that? With the vectors? Like, you can get to point B if you sum this vector with this vector. What does it mean by sum this vector with this vector? Like, you analyze this to x and y component and analyze this to x and y component. Some of them, they are going to give you the location of this point. Same thing with this one. X and y component and x and y component is going to give you how to get to this location, right? So this is how the vectors work, right? Like the same thing with the force. If you have a force, this length, F, this F is equal to, is equivalent to another F, this way, and this way, like F1 and F2. But you are going to tell me how. This is two forces, and this is much more longer. It doesn't work like this. You analyze this two components, so the component of this force is going to be something like this, and something like this. But the component of this force is going to be something like this, and something like this. When you sum them together, these two are in the same direction, so you are going to be plus, and these two are in the opposite direction. They are going to kill each other, and they are not be there, these two. Okay? So this is how vectors work. Same thing that I did here. Like, okay, like here, I went down and then went this way, and then I went this way and I went up. So this one goes down and this one goes up. They are killing each other, and I'm only careful. I only care about this length. So this is how the vectors work. Okay. All right. So same thing here. If I want to get RB, the position of RB with respect to A, like actually the position of B with respect to the origin. You guys tell me if I want to get RB to the origin, how can I do it? So you're going to say it's equal to RB from the origin to here. But I can't tell you it's equal to RA plus RAB, this one. RB is equal to RA plus RAB, and sometimes we call it plus RB with respect to A. Are you guys following with me? So RB is directly from the origin to B, or it's RA plus RAB, okay? All right. If I want to get the velocity of B, how can I get the velocity of B? B vector. I differentiate the position, right? How's the position? Is it changing over time? So it's a D RB vector by dt, right? If I differentiate it, how RB is it changing? Like at this point is here, at this point is here. So I have the position RB is changing. If I differentiate it with respect to the time, I will be able to get the velocity of point B. So can we differentiate this? It's gonna be dRA dt plus, I differentiate the first component and the second component, plus d dt to RB with respect to A. Well, you guys go back to the principles of rigid body. Does point A with respect to B can it change over the time? If it's rigid body, point A and point B are not gonna change with respect to each other unless this body is not rigid. Okay? So point A with respect to B, like this vector is never gonna change. The vector inside the rigid body. Like if I put a point here, actually let's make it here. So if I have here point A and point B, and this is a line between them. So if this body is moving this way, A and B position with respect to each other are gonna have the same length, same direction. Okay? So differentiating them with respect to the time is gonna end up with 0. Okay? So this is gonna lead us to that VB is equal to VA. Alright? And that's what we wrote here when we started the translation motion. VB is equal to VA for the two bodies. Alright? So this is the first thing that we have.
Can you explain one more time why equals 0?
Which one
The
equals 0?
RBA.
No, RBA has a value. Like RA with respect to B has a value. Like has a distance. Maybe it's a 6 centimeters or 6 inches. Okay? But it doesn't change over the time. This 6 is gonna stay 6. Okay? So when you differentiate this over time, all this equation, this RB cannot change over the time. Like if this body came here, like as a translation and moved this way, it become here. This is B and this is A. RB changes, RA changes. But A with respect to B or B with respect to A didn't change. Okay? So when you differentiate it over the time, it's equal to 0. Okay? So it has a value here but doesn't have a value here. Okay, so we can conclude to 3 things about rigid bodies under translation. Number 1, that V vector and the A vector, the velocity and the acceleration are the same for every point on the rigid body. For every point on the rigid body. Rigid body. Number 2, the omegas and the alpha, the angular motion and the angular velocity and the angular acceleration are always equal to 0 because there's no rotation. And number 3, which is the important one, that we can use same equations of particles with bodies, with rigid bodies under translation. We can use the particles equations for rigid bodies. So if I give you a rigid body under translation, you can use all the particle equations that we have to this rigid body. Like you guys had a car, had a body, had lots of stuff in the particles. They are under translation, so you can use the same equation for rigid bodies, the one that we learned from particles. Alright, so let's move to the fixed axis rotation. Chapter 16.3, fixed axis rotation. Fixed axis rotation. Let's imagine that we have a body like this, and this body is moving around an axis. Like the axis is something like this, and this axis bend here. So this body can move this way. And this body is 3D. Like if I take a cross section here, it's gonna be something like this, and this is the center. Right? And if I take the top view, it's gonna be something like this. Right? Okay. So this body is rotating and it has, for example, it has a theta theta is this way, as omega, as alpha, like this. And there is the axes. I have the x-axis this way, y-axis this way, and z-axis is going up. When this body starts rotating, let's define the dynamic quantities that we have. Let's say that this body starts from here, and or this point, and this point came here, or came here. Okay, so this point, I'm gonna call it point B. And if I want to describe the location of point B with respect to the origin, we call number one, let's describe the angular motion. As I said, angular motions doesn't happen with particles because particles are supposed to be very, very small. Okay, so angular motion happens with bodies. Okay, so it should be a body to have an angular motion. So something like this, or a line. If you have a line, this line can move and have an angular motion. Okay, so angular motion, it happens only for rigid bodies. Only for rigid bodies. Number two, angular position. How can I describe the position of a point on a rigid body? You should have a reference, which is the axis, and then this is the point, so we describe it with a theta. So this is a theta measured from the x-axis. If this point is on a general area, so it have a theta with x, theta with y, theta with z. So we will call here the angular position is defined by theta, measured from a reference. Number three is the angular displacement. What is the angular displacement? Let's say that this point starts to move again, and I want to measure the movement from this point to this point. So it came, for example, here. So the angular displacement is the difference between the final and the initial position. And it's going to be something like this, d theta, okay, between the final and like theta 2 minus theta 1. So like, for example, this is theta 2 and this is theta 1. So d theta is equal to theta 2 minus theta 1. All right, so this is the angular displacement, and we can call it d theta. Number four is the angular velocity. The angular velocity is v, and what is the value of v? Can you guys guess? Velocity is time rate of change, okay? And since we said angular, so it's time rate of change of the angular displacement, okay? So if we said linear velocity, so it's the time rate of change of the linear displacement. But since I have angular here, so it shouldn't be v. So we are gonna call it, the angular velocity is gonna be omega. Since I said angular, so it's gonna be omega, not v. If it's linear, so it's gonna be v. So omega is the time rate of change of theta. So d theta dt. Okay. The angular acceleration, number 5. The angular acceleration, we said it's alpha, and it's the time rate of change of the angular velocity, because we know that acceleration is the time rate of change of the velocity. And since this is angular, so it's gonna be the angular velocity. So this is gonna be d omega dt. All right. We're gonna do some stuff like we did in the first lecture of dynamics. Right now, we have displacement, or we have position, theta, we have omega, we have alpha. This is like S. Do you guys remember when we made a relationship between S, V, and acceleration? We are gonna make the same relationship with the angular position, the angular velocity, and the angular acceleration. So let's just start them here. And by the way, they are still in the equation sheet. If you look up there, you will find the general, you guys focus with me, okay? So the general motion equation, so you'll have general, non-constant V and A, and constant acceleration. This is for linear. You will find down same equations, but not linear. You will find them as an angular displacement, angular acceleration, angular velocity. So we need to make a relationship between theta, omega, and alpha. This is going to be similar to S, V, and A. Okay? Omega is d theta dt, alpha is d omega dt, right? So this means that d theta is equal to omega dt, and we are going to integrate from theta node to theta, and here from t node to t. So that means that theta minus theta node is equal to the integration from t node to t omega dt. We have same equation like this, but it was S minus S node is the integration from t node to t v dt. Okay, but right now everything is angular. Same thing with the acceleration. So you have that means that d omega is equal to alpha dt. I'm going to integrate both sides from omega node to omega, and here from t node to t, and this is going to be omega minus omega node is equal to the integration from t node to t, alpha dt. You guys remember the third equation? How we did it? There was a third equation. You guys remember?
The one without time.
The one was of time, exactly. So how did we build it? What we did, we take the acceleration equation, like alpha d omega dt, and we did a little bit of a mathematical tweak. We said that alpha can be equal to d omega dt, or I can say this is d omega d theta multiplied by d theta dt. How did I do this? Because I can cross d theta with d theta, and it end up with d omega dt. Or I know that d omega dt, omega is equal d theta. There's another way, like I can say that dt is equal d theta over omega and do something else. There was another way to do it, okay? So I know that d theta dt is equal to omega. So this is gonna be omega, d omega, d theta, and then I can say that alpha d theta is equal to omega, d omega. The one in the general motion, it was the acceleration, ds is equal to the velocity, v dv. Okay, same thing. So if we integrated both parts, here from theta node to theta, and here from omega node to omega, is gonna be half omega squared minus omega node squared is equal to the integration from theta node to theta alpha d theta. Alright, so this is the third equation. Okay? Alright, so the next step is you are gonna, this is the general equation. So if the velocity, yeah,
Can you write that equation up like on the top or like
is half multiplied by omega squared minus omega node squared equal to the integration from theta node to theta alpha d theta. Okay. So this is general equations. So if I told you that the velocity is constant and the acceleration is constant, we'll be able to solve this and solve this and solve this. And if they are not constant, so you are gonna keep them in the same form. But what if just the acceleration is constant? So if the acceleration is constant, so you can take the acceleration out of this equation and integrate d theta. You'll find all of them here, and you'll find them in the notes in the two different ways. If non-constant acceleration or constant acceleration, okay? So if it's constant acceleration, you are gonna take alpha out of here, and it's gonna be alpha t minus t naught. And you take alpha out of here, and it's gonna be alpha theta minus theta naught. And then you will end up with having the three set of equations down here. And you already have them here. So you don't have to memorize it, but it's better to know where it's coming from. All right. I want to do something on this body over there. So all right. So if I want to find the velocity, the linear velocity. So what we're talking about here is angular velocity. But what if I want to find the linear velocity out of the angular velocity? What does it mean, the linear velocity? So if this body's spinning this way, I can make something like this. I want to find the velocity, the linear velocity here. So how can I find the linear velocity? So let's write here 6 linear velocity. Actually, we did it, I believe, over something similar. Yeah, we wrote omega. So as we said, that the linear velocity v is equal to omega multiplied by the r vector. So if you know how much is the omega for this body, and if you know the r from the origin to this point and multiply them together, so you will be able to know what is the value of v. Something like this. So here, if I look at this from the top, so this is my point, and this is r. This is the r vector. And I know that omega is this way. So omega is going up. So this is omega. So if I multiply omega by r, can you imagine with me? Cross omega with r. So use your right hand rule. Omega is going up, and r is this way. Cross them together, so v is going this way. But if omega is on the other direction, so when you cross them up, so v is gonna go to the other direction. Right, but let me tell you something else. Do you know if you pick any point on the axis of rotation, like let's say a point here or a point here, and you connect to this point to point B, like if I did this here, so this is RB. So I can say that omega crossed by any r vector from the axis rotation is gonna give me the same thing. Why is that? Because as you guys know, from the inverse principle of the cross rotation, if you want to get the value of this, like the magnitude of the velocity is equal to the magnitude of the omega multiplied by the magnitude of RB multiplied by sine or cosine. What is the magnitude of the cross product? The dot product. If you have A multiplied dot product by B, so it's AB cosine the angle between them. The cross product is AB sine the angle between them. So this is sine phi. So the angle phi is the angle between the omega and the vector. So when RB sine phi, like if you find out the RB sine phi is gonna give you the same vector, like the value of the same vector. RB sine phi is the opposite here. So if the point is here and you connect it here, it's gonna be RB sine phi, and it's gonna give you the same one here. Alright? So if you pick any point on the axis of rotation and connect it to this point and multiply cross product with the omega, it's gonna give you the same thing. So why did we write r from the verse? So if we did r from the verse, sine phi is equal to 90 degrees. So 90 degrees is equal to 1. So v is equal to omega cross r. So there's different ways to get the linear velocity. If you know any distance between on the axis of rotation to this point. Okay? If you know this directly, that would be great. Right, so this is for v. So let's get the acceleration. Like right now we know the linear acceleration, so I'm gonna write it here, 6. Linear acceleration. Okay, linear acceleration, we said it's a v, omega crossed by r, alright? And that's what we wrote here actually. Omega crossed by r, omega crossed by ra, so it's always omega multiplied by the distance r. And we can make it general and we write rb, but let's remove it for now. Let's get the acceleration. And what I'm talking here linear acceleration, or not linear, let's say general acceleration. The velocity is linear, but the acceleration is not, let's say. So how can I get acceleration knowing the velocity? Here, we had an angular velocity, and then we said d theta dt, and the angular acceleration is the time derivative of the angular velocity. Same thing. The acceleration here is the time derivative of the linear acceleration. So if you want to find A, so it's going to be d dt of v vectors. So it's d dt of the omega crossed by the r vector. You guys can get this derivative? You guys tell me. How can I get the derivative of this? Two quantities multiplied by each other. Yes, what is it? How can I write it? So it's gonna be omega dot, which is the d omega dt r plus omega r dot, which is the dr dt. Right? Okay, what is the value of d omega dt? Look over there. Angular acceleration is equal, alpha is equal to omega dt. So here you'll have alpha vector multiplied by the r vector. Plus you have omega, and you have here dr dt, and I know r. Do I have r here? I didn't. dr dt. dr dt actually is this. Like v is the dr dt. Like if you have the time rate of change of the linear position is equal to the velocity. So here you can put dr dt is equal to this. So this is gonna be omega is equal to omega crossed by this. The time rate of the change of the linear position is equal to the velocity. Yes.
Is that supposed to say linear velocity instead of
Yeah,
acceleration?
because the velocity is going to be always linear. Is in
No,
the
I'm talking about
tangential.
on the like the little title that you wrote.
Yeah, linear. Yeah, sorry, this is linear velocity. Yeah, thank you.
No problem.
Linear. Right. So right now we have the velocity and we have the acceleration, and this is the components of the acceleration. So you have, and by the way, this is cross product, not dot product, because the r here are multiplied cross, and this is actually cross. So they are all cross product.
So the other one would be cross too? The other one is gonna be cross too?
This one is crossed. This one is crossed.
So what about-
Yeah, this one also is crossed. Since we have cross product, so the cross product is gonna stay. If they are multiplied dot product, so they are also after the derivative, all of them are gonna be dot product. All right. So this actually what we call the tangential acceleration, A tangent, and this is the normal acceleration. And this is similar to what we had before. Do you guys remember? The A tangent is equal to the A tangent, like it was, I don't know, do you guys remember the A tangent from before and the, okay, you guys remember the A normal, it was like V square over rho, right? And it's actually the same thing. Imagine with me. So, like this one, if you get the magnitude of all of these, like if we said the magnitude A tangent, is gonna be alpha multiplied by r, and the A normal is gonna be omega squared multiplied by r. As a magnitude, like here, this is the magnitude, this is the magnitude. So V squared over r, the V actually is omega multiplied by r, and all of them is squared, and rho is r. So you have omega squared, r squared, so it's gonna end up with omega squared r once you are done with that. It's gonna be something like this. Alright? So I believe this is most of the rules that we are gonna need to do the our first example in this topic. I'm not sure if it's hard, but I believe it's kind of similar to what we done before. Like this equation is the same that we have from the translational equation, but it just change it. B was omega, A was alpha. I believe we had some kind of stuff with the rotational motion, like omega and R and all this stuff. So just read the notes, and I believe you will get the idea, like how all this get together. Next time, or after 1 week, like after the next week, we're gonna continue this topic and solve an example and how we apply this on a real example.
Oh, that's the end?
Yeah. So you guys, there's 2 names here, 2 submitted Douglas.
Oh, I thought you were.
2 homeworks was submitted last time, and it's supposed to be go on campus. This is yours? Can you scan it and put it on campus?